use the Riemann sums.
All right. So we've got to finish 5.5 and 6.2. We might have to shorten the examples we do in 6.2, but we do need to talk about it. Before we start with finishing 5.5, do y'all have any homework questions? Okay, well then the example we were working on, we started off with the antiderivative of e to the 7x. And we're making a substitution. U is 7x. The inner function, the outer function is e to the x, or e to the power. And our derivative was 7dx, our derivative of u with respect to x. So we had to divide by 7. We have 1/7 du is e to the u times e to the u. And then we integrate that. I guess we looked at two different ways to approach that give you the same result. So did y'all have any questions on this?
No.
And then the next step is just to integrate 1/7 e to the u with respect to u. And then resubstitute. So there's our antiderivative. We resubstitute. Our u was 7x. Again, this is one of the antiderivatives on the formulas from 4.9. So the antiderivative of e to the ax will always be e to the ax divided by a. And it's easier to remember those than have to substitute. But if you want to substitute, we've seen a couple of examples where you can. So hopefully that all makes sense. Leave that up for a bit. All right. Gotta move. All right, a couple more examples. And then once we talk about how to find the definite integral using substitution, there's a couple approaches we can take. But the main thing to evaluate a definite integral is to find the antiderivative. That's by and large the hardest part. So here, example 5, we've got cosine cubed sine. What should our substitution be? Or do we need a substitution?
Probably in cosine.
Yeah. So if we let our u be cosine, and we're it's probably a toss-up when you first look at it because cosine's derivative is sitting there, the negative of it, and sine's derivative is also being cubed. But if we were to let u equal, if we were to say, well, let's let u equal sine of x, and du is cosine x dx, well then this right here has to go in. We don't have a cosine dx cubed. We just have cosine cubed. So we couldn't put that into the function because it's only cosine being cubed. So that wouldn't be a good substitution for that reason. And then so we try cosine, whose derivative is negative sine. Remember your dx here. When you take the derivative of u, remember your dx with that because you're really taking the derivative of u with respect to x and then moving that dx or multiplying through by that dx. So we have basically what's going on here is everything on the right-hand side of our substitution and our derivative, we want that to be present in the original integral. Since we have a positive sign and not a negative sign, we're just going to multiply through by -1. And we're using our substitution and this version of the derivative of the substitution because cosine and sine dx are in the original integral. So the cosine cubed sine turns into what? The antiderivative of u cubed so there's our cosine, and then the sine x was negative du, or negative 1 times du. So the negative 1 is just a constant that we're putting out in front of the antiderivative. So it's just the negative antiderivative of u cubed with respect to u. I put that in parentheses. Is everyone okay with that? Are there any questions? Okay, so we have u to the 4th over 4. Plus some constant, and then we resubstitute. So the antiderivative involves the power rule. And u was cosine. There's the antiderivative of cosine cubed sine.
So at what point did we drop sine from the original one? When did we stop using that?
Once we wrote in this negative du, because the sine of x dx is negative 1 times du. Any other questions on that? Yeah.
So I think you've already explained it. Why is du equal to negative sine x instead of just sine x?
Because when we take for the du, we're taking the derivative of our substitution, and the derivative of cosine is negative sine. Yeah, we'll always get those du's and the dx's by taking the derivative of our substitution. Try to remember to save in case the power goes out again. Okay, how about example 6? Is that a u substitution, and how do we know?
Because it's two functions of x, so you can...
It's two functions of x. And more importantly, remember the substitution undoes a chain rule. So in general, if you've got two functions being multiplied, the u substitution won't undo that. That's a completely different rule of integration. But it is true that substitution is applied when we have two functions of x, and more importantly, what else is present in the antiderivative? The derivative of one of the functions, or a constant multiple of the derivative is present. So if we let our u be x, we can't do anything else. We're still going to have this e to the, because the derivative of x is just 1. But if we let our u equal x squared, then the derivative of x squared is 2x. So that's a constant multiple of that other function sitting there. So if u is equal to x squared, then du is 2x dx. Again, we just want the stuff on the right to match what's present in the integral. We don't have a 2x, we have an x, so we're just going to divide through by 2. So we have 1/2 du is x dx. So this x times this dx, we're changing into 1/2 du. And we have e to the x squared, that's just e to the u. And we're finding the antiderivative of that now with respect to u. So we just have the antiderivative as 1/2 e to the u plus c. And then resubstitute. So it's the key is recognizing basically you're with these where you can see like a substitution, the function, one function in its derivative or a constant multiple of its derivative is setting there. Your outer function, the outer structure of that function doesn't change. So you can look at all of the substitutions that we've done, but like the square root is still present, the e to some power is still present, and you know the other variations on that, like example 7, it really depends on, you know, the ability to recognize a particular function and its antiderivative. Can I take the antiderivative of this function? Even if I substitute, it might not always yield something that I can take the antiderivative of. So, you know, it's not a perfect, straightforward one-to-one type of process.
Where does the x go from the x that's out front? Where does that?
So this x here, that x multiplied by this dx is transformed into the 1/2 du.
Okay, that makes sense.
Yeah. So again, if it were like x plus e to the x squared, you wouldn't need a substitution because we can, well, you would for e to the x squared, but you know, it's the format we looked at was that the integral of f composed with g times g prime. So it's again not only the product of two functions of x, but the inside function's derivative has to be present. And you know, as we look at different examples, we'll see that that's not always the case. It's just a matter of can you rearrange your substitution or the derivative of your substitution to account for everything that's present in the original integral. And there are functions, many functions that don't have antiderivatives. You can't write out an antiderivative for, if it were just e to the x squared, you can't find the antiderivative of this function. So nobody knows what that is, because there isn't a function that we can take the derivative of to give us e to the x squared. And there's lots of functions like that. We won't deal with those, but 7 and 8 are similar. Any ideas on question 7?
U should probably be 10x minus 3.
Okay, so I mean that's pretty much the only, we can't, you know, say that that's the log of 10x minus 3, right? 'Cause if we said that's the log of 10x minus 3, you know, plus c, if we check that, it doesn't quite check out, but it's close. So we have to use the chain rule and get the derivative of 10x plus 3 is 10. So if it were the antiderivative of 10 over 10x plus 3, then we could immediately say that it's the log of 10x plus 3.
And that right there actually gives us our answer because it's 10 times as much.
Yeah.
So if we multiply by 1/10.
Right. Multiply by 1/10. Right. So, you know, if maybe you're not thinking of the natural log and you just happen to say, well, the only function of x present there is 10x minus 3. Then just try that. There's nothing wrong with trying. Then the derivative of our substitution is 10 times dx. But again, there's not a 10 in the original integral, so we're just going to divide through by 10. And we've accounted for this dx here, and the 10x minus 3 there. we haven't accounted for the 1, but once you see, when you plug that in, it's just 1 over u times du. Do we know the antiderivative of 1 over u? Or u to the negative 1?
It's the natural log of absolute value of u.
Yeah, it's the natural log of the absolute value of u. Right, think about it backwards. The derivative of the natural log of u is 1 over u. Derivative of the natural log of x is 1 over x, so forth. And so we do want to leave the absolute value here because the u that we're substituting could be positive for some x values and it could be negative for some x values. So we just want to leave those there to ensure that that's always positive.
Do you multiply by that?
Oh, 1/10, yeah, where'd that 1/10 go? That 1/10 should be hanging out. Totally forgot.
Yeah. I was like, oh.
Yeah, sorry, I just forgot. And, you know, what we just erased was the fact that the derivative of that function is 10 over 10x minus 3. So if we take that function's derivative 10 over 10x minus 3 and multiply it by 1/10, we get 1 over 10x minus 3. Okay, so you've got a similar situation here in example 8, where you could look at your u substitution being u equals 1 over, or u equals 5x, or we could just say that's just 1/5 times 1 over x and move the 1/5 out. And then just find the antiderivative of 1 over x dx. We couldn't do that with the 10x minus 3 because wasn't just a single constant to pull out there. So this is 1/5 natural log absolute value of x. Let's see. You don't really need a u substitution there. Sometimes you do, it depends on the function of x that's down below. So having prior knowledge of antiderivatives is super helpful, especially when you look at, you know, ones like inverse tangent, ones like this, ones like inverse sine. You already have an idea of what that structure should be. Are there any questions on 7 or 8? So a pattern that, if you can recognize, is really efficient, and if you can recognize it, it's more efficient in the sense that you don't have to do a u substitution. If you're not able to recognize, it's fine because then you can just default to a u substitution. Is the form of f prime over f, which we know comes from the derivative of the natural log of some function via the chain rule. So since we know that from the chain rule that that's true, then what we know is that the antiderivative of the derivative of a function over the function will just evaluate to the natural log of the absolute value of f of x.
And those two functions are the same, like the derivative is the top function is the derivative of the bottom function?
Correct.
Yes. Correct,
yeah, it has to be derivative over the function in order to be in the form of a logarithm, the natural logarithm. So, you know, something like this, for example, if you recognize, well, if I look at either one of these functions and look at their derivatives, and I say, well, the function on the bottom, its derivative is up top, right? Derivative of 2 times e to the 3x is 2 times 3 times e to the 3x, which is 6 e to the 3x, and 20 e to the 4x. So if you recognize that, then what we've been doing is saying, okay, well, I'm going to let u be that bottom function, whose derivative is also present in the integral. Then, you know, go through that entire process of u substitution. Or it's more efficient to recognize this format and say, well, the function on the bottom is, its derivative is up top, so I know without even doing a u substitution that this is just going to be the natural log of the absolute value of that function on bottom. And if you want to do a u substitution, you can do that just to verify, but it's the same exact result. I don't think it's necessary to recognize that pattern. If you just go through the process of u substitution, that's good enough. But it's helpful if you can. And in fact, the the antiderivative of tangent and cotangent can be viewed through that same idea. We haven't talked about the antiderivative of tangent or cotangent. We looked at the antiderivative of sine, cosine, secant squared, stuff like that. But if we look at tangent as sine over cosine, and we say let u equal cosine x, just like in that other problem, negative du is the sine of x with the cosine cubed times sine. Then what we end up with is a means to integrate or find the antiderivative of the tangent function, because we have negative du for sine dx divided by u. Or another way to write that, the negative out front, the 1 over u here, and then the du here. Same thing. So again, what you have is the antiderivative of 1 over u, which is the natural log, but it's negative. And our u was cosine. So that is the antiderivative of tangent. In other words, that if we take the derivative of this function, we'll get tangent as a result. Cotangent's very similar. It's more straightforward because it's cosine over sine, and u is sine. You don't have a constant to move to the other side. But that particular logarithmic format, f prime over f, is really common. Maybe not so much for this class, but definitely shows up. Does anyone have any questions on that? Okay. So how about this one? What's the antiderivative of that? What does it look like? Sort of, maybe.
It's the one, it's not inverse sine.
It's not?
Is it? Am I right on that? Because it should be 1 squared with the x squared. Square root of square root of a squared minus x squared, right?
Right.
Is that
That's
inverse sine? I
Yep.
nailed it.
So if you don't know that, then at some point you're just going to be totally stuck with this problem. I guess there's two ways to look at it. One of the ways to look at it was through how we might approach it in chapter 4 without being able to substitute. So let's look at that from chapter 4. What we would do is, and here's what we're thinking about overall, is this. Is this right here. And if we're looking at that formula from 4.9, the issue is we don't have you know, an a squared minus bx squared, right? It's just a squared minus a 1x squared. But we don't have a 1x squared with this 9x squared. So what we're going to do in order to force that to be a 1 in front of the x squared is we're just going to factor out a 9 from the 1 minus 9x squared. So we would have to rewrite it. So we have this x squared here, this 1x squared here rather. And then we're factoring the 9 out of the 1 as well. We would have a 1 over 9. So we have on the bottom, the square root of a product. We're just going to take the square root of 9 and take that out as a constant. So the square root of 9, square root of 1 over 9 rather, is 1/3. And then our root 1/9 minus x squared still left. So now, from just factoring that 9 out, we see that this antiderivative fits the one on the table from 4.9. So the a is what? Is 1/3. Because that 1/9 is representing the a squared. So we'd say that's 1/3. The antiderivative of that thing with a being 1/3 is the inverse sine of x over a plus c. Or 1/3, yeah, inverse sine of 3x. So that's how we handled those in chapter 4. We did maybe one example in class, and I know there were a couple in your homework where you had to factor something out to get it to look like inverse sine or tangent. So the other way to do so, does anyone have any questions on that? Kind of revisiting how we did that in chapter 4. The other way to compute this now through chapter 5 in substitution is we're going to say, all right, well, isn't that the same thing as 3x quantity squared? And then we can say let u equal to 3x. So what's the derivative of 3x is going to be just 3. There isn't a 3 present in the rest of that integral, but again, it's just a constant, so we can kind of scoot it to the other side. So du is 3 dx, and 1/3 du is dx. So let's see how that actually helps, or if it does help. When we plug in for our 3x is u. This is still the square root of 1 minus that. And then we have our 1/3 du replacing that dx. Does that help? if we ask the question, what's the antiderivative of 1 over the square root of 1 minus x squared with respect to x, what would you say?
Inverse sine.
Inverse sine of
X.
x over a, which is 1, right? But this is the inverse sine of x. What is this one here?
The inverse sine of u.
It's just the inverse sine of u. We're just using a different variable. So that's 1/3 times the inverse sine of u plus c. And u was 3x.
Shiny.
But again, substitution or methods from chapter 4 only go so far. You have to know that that particular function is inverse sine. If you take Calc 2, you'll learn a technique to figure that out. But it's probably going to take you at least 5 minutes to get through all of the work to show that in fact is inverse sine. If you just remember it's inverse sine, that's all you need. So, there are any questions on that example? So we're going to look at this example because certain types of functions, initially when you look at it, a u substitution may not seem to work. But the overall goal in substituting for anything is just to end up with something simpler that you can work with still. So maybe it's not totally obvious, but anybody have any ideas on what our substitution should be?
Do you even need substitution?
Do we even need substitution here?
You just use the f prime over f, right?
Well, so the derivative of
That's,
x minus 2 is 1.
One, yeah.
So the derivative of the bottom
Oh,
isn't
yeah.
sitting up top.
Okay.
Should break it apart though.
Could we break it apart?
X over x minus x over 2.
So when we can break things up is when it's the other way around. If this were x minus 2 over x, then we could break that up. We don't recognize it as a known antiderivative. It's not in that logarithmic form. It's not something we can simplify. So if that's where you're at in Calc 1, then your only other option is to try u substitution because that's all your techniques right there. So it's good to have a limited set of techniques because you're not wondering which one should I use. If you had a dozen integration techniques, then you might think, okay, well, will this one work? Will this one work? Will this one, right? Sometimes the more choices you have, the worse off you are. So we've exhausted those possibilities. U substitution might work. So what should U be? I don't think initially there's a right or wrong answer. It's just one of those things has to be U, and then we go from there to see, does that give us something that we can find the antiderivative of?
Essentially, whether you use the top or the bottom, you're going to get the same du, aren't you?
Right.
So does it even really matter?
Yeah, so does it matter? Let's see, what happens if U is equal to X?
Du is just equals
1 times dx.
dx.
Okay, so then basically what we're looking at then is this right here. We've got to account for this x minus 2, but this is all our substitution and its derivative has done. So how do we account for the x minus 2 if that's our substitution and that's our derivative?
You can't make that u over u minus 2.
U over u minus 2? Yeah, we could do that, right? Because u is equal to x.
Yeah, can you do
So
that?
what if we said this is
that
just
okay?
u over u minus 2 du?
I guess we're right back where we started.
Right, it's the exact same, we just changed a variable. No, you're thinking about it and it's good.
What if you, hold on, if you Because if you would be able to just say x minus 2 to the power of -1, because then if you use your antiderivative rules, you have zeros.
Yeah,
Anyway,
right.
right, so it wouldn't.
Right, and then we never want to mix variables like that either. If we're going to change everything in terms of u, then everything needs to be in terms of u, not u and x. I mean, everything is based off of the original substitution, right? Even the derivative is based on the substitution that I chose initially. So we say, well, if u is equal to x, then we might could say, isn't u minus 2 equal to x minus 2? Couldn't I just subtract both sides from my original equation that I substituted u equals x? I just subtract both 2 from both sides. But again, I'm in the same position as if I were to let x be u, right? It's still of the format x over x minus 2.
Are we allowed to adjust like the x over x minus 2 so that like everything's on top and we can try to get one single x?
Yeah, so you could rewrite the original integral as x times x minus 2 to the -1, like that.
Yeah, then. Does that help at all?
Could you just say, hold on, what if you,
So that
could you have your final answer, I guess, could you have, shit, I don't know if that worked either. Because if you use u on the bottom, you would then have x over u times du, right?
Yeah,
Yeah.
and we'd have to account for x itself.
Okay.
Yeah, so we tried the top, let's try the bottom. U is x minus 2, still the same derivative, du is dx. But how do we account for the x that's on top?
You could say u minus 2.
Yeah.
Plus 2.
Oops. Okay, so if our u is x minus 2, then we can just rearrange that equation. U is x minus 2, what that means is we're solving for x. U plus 2 is equal to x. So rewriting x as u plus 2, does that help? Yeah, why is that better than what we started with? Because now you can split the integral in terms of u up. We couldn't split the integral involving x up. So now we have just u over u plus 2 over u. Oh. And we're just going to simplify that. Can we find the antiderivative of 1? Yeah. Can we find the antiderivative of 2 over u with respect to u? Yeah. What's the antiderivative of 2 over u with respect to u? Yeah, it's 2 times the natural log of u.
2 times the natural log of the absolute value.
Of the absolute value, right? So we're just going to, the 2 is a constant. We're going to take that out front and integrate just 1 over u with respect to u. So that did help. It just initially didn't look like it was going to help making that substitution. Okay, so the antiderivative of 1 is u. We have 2 times the natural log of the absolute value of u. And then we're going to resubstitute. Our u was x minus 2. So then, I guess the upside of antiderivatives is that you can always check your work. So let's check this one. If that's the antiderivative, then when we take the derivative of the antiderivative, it should be the original function. So that's what we're going to try to verify. The derivative of x is 1, minus 2 is 0, plus 2 times the derivative of this is 1 over the argument, times the derivative of the argument, times 1, and the derivative of our constant is 0. So we have 1 plus the quantity 2 over x minus 2. In order to add those together, we're going to write 1 as x minus 2 over x minus 2. So we have a common denominator. We have x minus 2 plus 2 up top over x minus 2, which is x over x minus 2. So I also wanted to point that out because sometimes when you take the derivative of your antiderivative to check, it doesn't always come out exactly how your antiderivative looks. Sometimes you have to simplify things or combine things in your derivative, like we did here, to actually verify that it is the same. The other technique that you'll learn is that when you have what they call is rational type functions, well, one polynomial over another, like x over x minus 2, and the degrees are the same, they call that improper. So we could take this one here and go through the process of long division. What's x divided by, what's x divided by x minus 2? When we divide x by x minus 2, this is what we end up with. X divided by x minus 2 is that. So through the algebraic process of long division, we could have said that this thing here is equivalent to this thing here, just through simplification. And then again, you're in the same position. What's the antiderivative of 1 with respect to x? What's the antiderivative of this? 2 natural log x minus 2. So we know this thing right here. Well, I should maybe not say that. Yeah, I won't say that for now. But it's well beyond it's well within our capabilities to divide x by x minus 2 and express that as something divided by x minus 2 plus something else, which would break that down and allow us to find the antiderivative. So it's not that you're limited to use substitution in an instance like this. Again, antiderivatives are hard. There's not one clear-cut process. If it's this, then sometimes this thing will work. If it's this, sometimes something else will work. Sometimes 3 things will work. It's really just like a trial and error, especially when you're starting off. So if you look at something and you're like, I don't even know where to begin, then just try a substitution and see, does that yield something I can take the antiderivative of? If it doesn't, then pick something else and substitute in for that. So sometimes more than one u substitution will work. So for a problem like this, if we let u be x plus 1, then we're going to be able to substitute that and find the antiderivative that way. Or if we were to allow our substitution to be the square root of x plus 1, that will also work. So both of those substitutions will work. We'll get the same result at the end, but you'll end up with a slightly different antiderivative involving u, both of which can be done. Okay. So in the original integral, if we're going to let u equal x plus 1, then we've got the integrals 1 over the square root of u. We've got to account for the dx and the x up top. Similar to that last problem, when we look at the derivative of our substitution, we just get dx. So we can account for this piece and this piece. We'll take the original substitution and solve for x. So we have the top x being u minus 1 over the square root of u. Dx is du. So you're kind of in the same position where that last problem we had, a couple of terms divided by a single term. Whenever you're looking at an integral like that, you want to split it up. Typically, you want to split it up. So we could write it like this: u over root u minus 1 over root u. Some people will say that this is u to the negative 1/2. So we'll say this is actually u minus 1 times u to the negative 1/2, and simplify it that way. It doesn't really matter, you end up with the same thing. So everyone, has a bit of a different approach. One or the other is typically most common, I would say. But if you're going to split it up like this we did initially, then you've got u to the first divided by u to the 1/2, right? You're subtracting the exponents. Then you're going to turn in 1 over the square root of u just into u to the negative 1/2. Here we're just going to distribute the u to the negative 1/2 through. Either approach that you take, splitting up and then simplifying, or writing the square root as u to the negative 1/2 and then distributing. Either way, you're going to get here where you're just integrating powers of u. So that's u to the 3/2. Add 1 to the power, divide by the result. Dividing by 3/2 or multiplying by 2/3. Minus the antiderivative of u to the negative 1/2. So add 1 to the power, divide by the result. Dividing by 1/2 is multiplying by 2. So just for space purposes, just put that here. And then we resubstitute. So that would be the antiderivative. Do y'all have any questions on that? So I'll leave the other substitution to you if you want to verify, but using the substitution u equals to the square root of x plus 1, notice where that would leave you if we did this. We still have to account for the x and the dx. So do we want to just take the derivative of u as it is? If you do, then you have to use the chain rule on this. Right, and then so that just introduces a layer of complexity that we didn't have or didn't have to account for in the what's left over, right? Because all we have to account for is the x and the dx. Sorry, dx over here. So if you were to take the derivative of your substitution here and get this thing, you might say, well, that's not helping me account for just an x, the x on top. Yeah, I have the dx in here now, but nowhere near 1/2 x plus 1 to the negative 1/2 is left over. So we might say, well, let me just scrap that. And based on my substitution, try to account for x. So if u is the square root of x plus 1, then u squared has to be x plus 1. Which means u squared minus 1, oops, u squared minus 1 is equal to x. And then we can take the derivative of this thing right here. So we've accounted for the x. So we're going to have a u squared minus 1 over u dx. You've got to now involve the derivative somewhere, somehow, to account for the dx. So if we involve the derivative here, we say the derivative of x with respect to u. Right, here's x as a function of u. What's the derivative of x with respect to u? What if I had x squared minus 1 is equal to y? What's the derivative of y with respect to x?
2x.
2x, right? So what's the derivative of our function x with respect to u?
2u.
2u. In other words, 2u times du is equal to dx. And so we can account for our dx this way, we can account for x this way, and we have our original substitution accounting for the root. So those are the components that we would use there. And it's not saying that it's an easier substitution, but both of them do actually work. So we write this here. Dx was 2u du. The square root of x plus 1 was u. And x was u squared minus 1. So here with this substitution, you've got this u divided by this u just cancels out. The 2 comes out front of the u squared minus 1 du. So again, you're just integrating powers of u at that point. So it's 2u times u cubed over 3 minus u. No, and whatever, we'll have our constant out here. And then when we plug that substitution back in, u was the square root of x plus 1. Cubed over 3. So notice this first term here, that's the same thing as 2/3 times x to what power? What's the square, x plus 1, the square root of x plus 1 to the third, how else can we rewrite that? The square root of x plus 1 cubed is the same thing as x plus 1 to what power? To the 3/2, right? So you got 2/3 times x to the 3/2. 2/3, or sorry, x plus 1 to the 3/2. Second term should be -2 square root of x plus 1. 2 times that is -2 square root of x plus 1. So yeah, I don't know that second substitution it would be as common as maybe the first one, because the first one was a little more straightforward. But again, oftentimes more than one substitution could work. That's the whole point. Do y'all have any questions on any of that? Okay, so let's talk about definite integrals. We're only just going to look at this one particular for definite integrals, because again, the biggest portion of these things is finding the antiderivative. So there's a couple of ways to approach this. When we were using our u substitution to find the antiderivative, we ended up with an expression involving u, and then we resubstituted for x. So one approach is to find the antiderivative in terms of u, and then resubstitute for x, and then use the bounds from 0 to 2. So since we're starting off with respect to x, these two bounds are for our x values. The other option is we could just rewrite this integral in terms of u, and then rewrite our bounds in terms of u and deal with that, because it will give you the same net area. But the first thing is to find the antiderivative. So we're going to find the antiderivative of that and then worry about the bounds after. So we don't know a function whose derivative is 1 over x plus 3 cubed. So what should we try from here?
X plus 3 is u.
X plus 3 is equal to u. Let's try it. U is x plus 3. Derivative of u with respect to x is 1 dx. So from here, we just end up with the antiderivative of 1 over u cubed du. So we haven't necessarily found the antiderivative, but it's at this stage that we have the two options. Either we can carry through with this and then resubstitute for x, so we can use the bounds from 0 to 2, or we can look at this thing here and say, well, since I'm dealing now with an integral with respect to u, I'm going to change my bound 0 and 2 into a u value instead of an x value. So option one, we're just going to say change the bounds. Of x being 0 and 2. Change those to u values using the substitution. U equals x plus 3. Some people don't like to do this, others do, so we're just going to look at both. That way you can decide which one you want to stick with. I can always guarantee that if you use the values for u in the simplified integral, that you'll always have a simpler problem to deal with, as opposed to resubstituting and using the original bounds. But it's totally up to you. So this is 1 over u cubed du. And if u is equal to x plus 3, we've got two x values. When x is equal to 0, u is equal to, when x is 0, u is equal to 0 plus 3. So that was our lower bound when x was u. That corresponds to a u value of 3. And when x was 2, u equals 2 plus 3, which is 5. So that's our upper bound. Does that make sense? Because it's by far the easier way to do these two things. The other option is to find the antiderivative in terms of u, and then resubstitute for x, so you can use 0 and 2. Find the antiderivative in terms of u. Resubstitute. Resubstitute u x plus 3 for u, and then use the original bounds of x equals 0, x equals 2. Alright, so if you need to rewrite that, we'll look at that in a moment. So we've changed the bounds in terms of u, and we've got the antiderivative of this. This is just the same thing as the integral from 3 to 5 of u to the negative 3. So we add 1, divide by the same result, and this time it's a definite integral, so we're not going to add a constant, but we are going to evaluate it from 3 to 5. I'm going to take that constant out. Just evaluate 1 over u squared from 3 to 5. Okay, so remember the fundamental theorem, we plug in the upper bound first. subtract off the antiderivative evaluated at the lower limit. So you have common denominator, et cetera. That's 8 over 225. Questions on that? Naturally, if you mix your bounds up, if you integrated 1 over u cubed from 0 to 2, the final answer is just going to be way off. So your bounds and value need to match the variable you're integrating with respect to. We didn't really change all that much from the original function. The original function was from 0 to 2 of 1 over the quantity x plus 3 cubed. I mean, we've got a very, very similar integral here with just 1 over u cubed. So there's the original integral. We're finding the area from here to 2 underneath that curve in the x-axis. We won't be able to do u, but notice if we looked at the function 1 over x cubed, from 3 to 5, different function, different region, but what we're saying is that this area here, a slightly simpler function, it's just 1 over u cubed. That area there is the same as this area here. There's another one in your textbook. So here's another kind of geometric visualization, if you will, of a u substitution. So instead of integrating from 0 to 2 on 2 times 2x minus 1, which would be this region on the left, once we make a u substitution, we integrate from 1 to 5 of just u itself, which is just that line through the origin. So it's a slightly simpler function. They're pretty comparable, but the areas of r and r prime are exactly the same. All right, let's take a break.
Second that motion.
They would, I'm pretty certain they would happily take you right up to the last second.
I just don't know if I have time. But I would
It's
love
usually,
to do it.
yeah, so you sit in class, so that's 4 hours a week. Yeah. But the nice thing is, you already got your notes starting on material, and you are not required to teach the material. What you're going to do is you're going to warn people.
All right, I just want to mention this last bit in 5.5. Not necessarily you won't see this in Calc 1. I mean, you could, but definitely if you go on, you'll see these two integrals quite often. They're not directly a u substitution as they are. These two are u substitutions when we remember the identity for sine squared as 1/2 times the quantity 1 minus cosine of 2 theta. And then that cosine, when we integrate the right-hand side, the 1/2 times 1 minus cosine 2 theta, that cosine of 2 theta technically is a u substitution, but again, hopefully you remember what the antiderivative is. And for cosine squared, sorry, let's 2x. Cosine squared is 1/2 times the quantity 1 plus cosine of 2x. And then so instead of integrating sine squared or cosine squared, we integrate the expression on the right. So, you know, like for instance, this one here, we're now able to split that up into two different antiderivatives. And so that's the constant we'll just take out because we can take the antiderivative of both of these terms. So what is the antiderivative of the cosine of 2x? Antiderivative of 1 is x minus the antiderivative of cosine 2x.
Sine 2x over 2.
Yeah, sine of 2x over 2. Antiderivative of the cosine of ax is sine of ax over a. So there's your antiderivative. That's 1/2 x minus 1/4 sine of 2x. So the only thing different with the other identity is that we had a plus in front of the cosine 2x, so it's the same antiderivative, but it's got a plus instead of a minus. A lot of the integrals involving trig functions can get tricky because there's just so many different ways to represent them. Right, you saw that with like trig, proving trig identities. But definitely sine squared and cosine squared, worth remembering those two identities there so you can find the antiderivative of them. And honestly, I think they show up often enough to where if you just want to remember what those are, I think there's nothing wrong with just remembering what those are, because they are very common. I won't have those on the test by themselves. You could have like one we did earlier was like cosine cubed times sine and have a u substitution there. But as far as like sine squared and cosine squared by themselves on the final, they won't be there. But I think for sure well worth knowing those two. Are there any questions on 5.5? Okay. We'll kind of briefly talk about 6.2, which is regions between curves. And when we looked at our Riemann sums, this thing down here, the integral from a to b of f of x dx, what we were dealing with in that situation was this is a specific kind of form that we'll look at in a moment. But we had some function that was bound from a to b and the x-axis. So we said what's the area or the net area in general of this region here, and that's what's given by our Riemann sums in that particular form. Okay. And so the way we did that, the way that formula came about was we said, well, pick or slice that region up into a bunch of different rectangles and compute the area of each rectangle. So remember we said that the height of the rectangle was determined by the function. That's the height of that rectangle is f of x. So more generally, what we can talk about then is, what if we had two curves? This is g of x, and this is f of x. The way we find the area of something like that is identical. We cut it up into a bunch of pieces, and then we look at the area of each rectangle. So like, let's just say we focused on that rectangle there. The thicknesses are still some predetermined x value, or we could let it vary, but the thicknesses are still delta x, which will turn into a dx. But what's the height of this rectangle here? And what's the height of this rectangle here? How do we determine the heights of each rectangle now?
F minus G.
F minus g, do y'all agree with that? Because in the chapter 5 stuff, we were saying, you know, like, what's the height of this point? And so all we're doing is measuring that distance from this y value to a y value of 0. So it's always evident, like if that were 5, it's evident that that distance is 5, right? So what we're doing is, in chapter 6, is we're saying, okay, well, what if I have this curve here and this curve here, and I want to know what this height is? Well, if I knew this y value was 7, and I knew this y value was 3, then I know the height is 4. But honestly, all you're doing in either situation is you're saying what's the height at the top of the rectangle, or what's that value, subtracting off the lower value of the bottom of the rectangle, if you will. So in order to find the area between two curves, what we're going to do is just modify the height of each rectangle. So it's the integral from a to b, f of x minus g of x is what we're integrating now with respect to x. So you can just think about that as the top minus the bottom for the heights. The height of each rectangle is just the top minus the bottom. Since the top is bound by a function, the bottom is bound by a function. It's the top function minus the bottom function. If we go back up to what we've been doing, you know, really what we're looking at with this integral is that it's the integral from a to b of f of x minus 0, because the bottom of the region was always the x-axis, and that always has a value of 0. So it's a more specific case of this type of situation that we were looking at prior to this. So typically the complications with these types of things is not in knowing what the top minus the bottom is, because those two functions are given to you. But if we say that we're going to evaluate or determine the area from A to B, that's generally not given to you what A and B are. So a lot of the difficulty with this arises in finding these points of intersection. And once we know this x-coordinate of intersection here, that's our A, and the x-coordinate of intersection here is our B. So a lot of work sometimes is involved in determining where those points of intersection are. Now, the same could be said if we were to rotate this region 90 degrees, we can evaluate this with respect to y, and it's the same kind of situation. So we could have a region that's like, here's f of x. Sorry, f. Let's label this in a minute. It could be a function of x, but I'm going to think about it a little differently. So let's just call that g and f. And instead of slicing this in a vertical way where our rectangles are running up and down, we could do the same thing where the rectangles are running from right to left, left to right. And the idea is still the same. You take the area of all of those rectangles and sum them up. But in exaggerating this rectangle a bit, it no longer has a thickness dx, it now has a thickness dy. So we could integrate with respect to y. We could integrate this region with respect to x. It's the same area regardless of, whether we cut it up this way or this way. It doesn't matter. But in this instance, we're thinking about the height now running left to right. What's the height of each rectangle here? Do what?
F, y, and g of y.
Yeah, how do we combine them? Like, what if I knew this rectangle went from here to here, and I knew this value was 5, and I knew this value was 8. How tall is that rectangle? 3 units, right? So we take 8 minus 5 and we get 3. So the height of each one of these rectangles going this way is just simply the function or the curve on the right minus the curve on the left. And so we integrate, we'll use different bounds. We'll say from C to D, just so may not necessarily be the same for the, and the function on the right we had was f. So that's some function of y now, because we are integrating with respect to y. The right function minus the left function for the height, and dy for the length of each one. So there's height times length for the first rectangle, the second, the third, the fourth. Here's our infinite sum. And we would say maybe this point is C, and this point is D. Hopefully that just makes sense intuitively. It doesn't matter if you look at it like this or if you look at it like that. It's the same area. So on the final, there's going to be one question from 6.2. The graph will be provided, but the intersection points won't be provided. So we're going to look at a few examples. There's no way we can get through all of this. So it says find the area of the region between x cubed, x squared minus x on the interval 0, 1. So you really have to take into account what's the area that's shared by all of those curves and the specified, starting and ending points. So we're starting here at this x value, and we're ending here at this x value. So that's kind of like our wall right there. Now, they share other areas, they like this area in between the curves here, but that's not the area we're looking for, because we're only focusing on the interval from 0 to 1. So we're just going to highlight these curves and say, what's the shared area between what I have highlighted here? A lot of the issue here with even if graphs are provided, people will determine the wrong shaded region. So we want to make sure that the area is bound by all of the curves that are specified, which is this area right here. So we're after what this area is bound by, x cubed, x squared minus x from 0 to 1. So that's what we're looking at. Again, we're just imagining filling up this region with rectangles. So anyone want to take a shot at how we would compute the area?
Is it with the trapezoids?
No, we're not. We wouldn't. We could use trapezoids. We're just going to use rectangles. So if I'm looking at this in terms of x, where does my rectangle start and where does it stop? If I fill in that whole region up with rectangles. Right. I start here. That's an x value of 0, and I end here. That's an x value of 1. Does everybody agree with that? So it's the integral from 0 to 1. Is 0, that's 1? Of what?
F of 1 minus G of Y.
F of x?
F of x minus G of X.
So how do we determine the rectangle's height that are running up and down?
You take the top function, you subtract the bottom function.
Take the top value minus the bottom value, or here, the top function minus the bottom function. Okay, so be careful here. That's the height of each rectangle, but since we're subtracting off, you need to subtract off the entire function. So that's the height of each rectangle and the thickness of each rectangle. So really the function involved in that integral is always the top function minus the bottom function, or if they're running the other direction, it's the right function minus the left function. Okay, so looking at that setup, is everyone all right with that? Are there any questions? Okay, so we're just integrating powers of x there, so. Should come out to be 5/12. No one has any questions? I'm going to go to example 3. And this example is showing us, like we could integrate with respect to y or x. Why would we want to have two different methods when they both would give us the same result? This is an example of why it's more beneficial to have multiple methods. Because if we tried to integrate this with respect to x, then all of our rectangles have to do this. And then so we have to say, well, these rectangles have some thickness in the x direction. We're integrating everything with respect to x. So we would have to take this function. This is x equals to y cubed minus 4y. We have to take that function and solve for x. Or solve for y, right? Because if we're gonna integrate something with respect to x, we have to have a function of x here, or things, or y equals to, right? It's not a trivial thing to solve for a cube. So solving for the y cubed minus 4y would be super difficult. And what you would see is that if you solve for this g of y function, if you solve for y, you actually end up with 3 functions, and those 3 functions are going to end up making up this this curve right here. So we know that's not a function, but if we solve for y and we say y equals to all of this stuff involving x, then essentially what it is you've got three different functions of x. So maybe this part of the curve is one function of x. This part of the curve is another function of x, or whatever it may be. And this part of the curve is the third function. So since it's not easy to solve for y, so we can't integrate with respect to x, we have the other approach. Now, we don't have to look at it that way. We can look at our rectangles running this way, and then when we do, it never, the right function and the left function never really change. Because like if we were integrating this with respect to x from -2 to 2, like how would we determine this height? We would say, all right, well the height right there is just the top function minus the bottom function. Okay, but what about the height of this rectangle right here? It's the same function minus itself. I mean, we really couldn't even do that, right? So you can't determine, even in that instance, what the height of this rectangle is when things are expressed in terms of y. But if we look at it with our rectangles running the other way, in this entire region, it's always just going to be the right minus the left, right minus the left, all the way through. So here's y equals -2. I know the graph isn't great. That's y equals -2. This is y equals to 2. From this statement right here. That function on the left is the y cubed minus 4y.
So the right function is h of y?
Yeah. So I think it's super important to have a region and to know like what region you're focusing on is the region shared by all of these curves, what they have in common, which is all of this stuff here. So we're finding that area. And it's helpful to visualize that if we're going to integrate with respect to y, that all of our rectangles are running this direction. And no matter where we are, the height of those rectangles is always right minus the left. Much easier to integrate this with respect to y than it ever would be to integrate with respect to x. So if you're not like looking at your picture or drawing pictures out, chances are that you're going to mess something up. If you go on to Calc 2, then you take regions like this and you revolve it around an axis and then you compute the volume of that thing. So this is, the methods that we're talking about here are directly related to those methods. So we've got the region, we've got our, you know, the picture drawn out so we can clearly see what's happening. Does anyone want to say what the area would look like?
Do you want the way to get it? Like
Yeah.
start to finish?
Yeah, the integral from,
All right, so it's going to be big S 2 to -2. And then
2 to -2, so make sure the smaller one's on bottom.
Yeah. And then you're going to want your top one, y to the third plus y to the second plus 8.
Okay.
Is your y to the third minus 4y.
Okay. Again, we're subtracting off the whole function, so make sure you've got something there to indicate so you don't mess up. What do y'all think about that? The height of each rectangle? Does that look okay? Our rectangles are running left to right, so the height's always the right function minus the left. And we're integrating, excuse me, with respect to y. And just exaggerate these rectangles a bit. That right there has a thickness in the y direction. So then you're just going to combine like terms in there and integrate powers of y. It's 112 over 3. So hopefully here what we're doing isn't too far of a stretch as opposed to what we did do in chapter 5. Again, the only thing that changes here is the function you're integrating. That depends on whether your rectangles are running horizontally, which it would be the right minus the left situation, or if your rectangles are running vertically, it's the top minus the bottom situation. Do y'all have any questions on that? Okay, I want to go back to this example here. So the area of the region bound by the three curves, 8 over x squared, 8 over x, or 8x rather, and x. So our 8 over x squared is this function here. 8x, this function's here, and x, this function here. So we're finding the area that's shared by all three of those. I'm just gonna pull this up here. So we've got to find the area of that thing. So notice if, we're just visualizing or drawing this out physically, if my rectangles are running like this, can we get all of that area with just one integral? Yes?
Yeah.
No? Somebody saying no? Eric, why are you saying no?
Well, because you have to subtract the bottom function x from two different ones, from 8x and 8 over x squared.
Right. Does everybody see that?
One integral.
Like if these are my rectangles, it's fine for that region because we have this top function minus the bottom function. But after this point right here, what happens?
Your top function changes.
Your top function changes, right? So if I look at that rectangle, now the top minus the bottom is determined by one completely different function, because the 8 over x squared is now the top function.
So would be the 8x minus x plus the 8 divided by x squared minus x?
Right,
Basically,
yeah.
Okay.
So you've actually, since the top and the top function changes as we transition through this dotted line, you actually have one integral to describe the area on the left and another one to describe the area on the right. So if I can
given the interval? Are you given the interval?
No, you're not given an interval.
Okay, so we do have to find the intersection point.
You do have to find the intersection points. So we have this area plus this area. That's how we have to look at that region. Anytime the top function or the bottom function changes as you move your rectangles, whether that's, you know, side to side or up and down, you've got to have a different integral that describes it because you have completely different functions you've got to integrate. So I think this intersection point here is pretty trivial.
Origin.
Yeah, it's just the origin. What is this intersection point and what is this intersection point? We need to know those two because in that first region, we're going from an x value of 0 to this x value. Whatever x value is described by that point right there is that right there. Is where we're ending. And whatever x value this is right here is where the second region starts. The second region ends at this other point. So let's find the points of intersection. Leave some space here. We'll just call this region 1 and we'll call this region 2. Points of intersection for region 1. How are we finding the point of intersection, that gold point? We'll draw it up here too. That's where what two functions intersect?
8x and x over x squared.
Yeah, 8x, the line, and the curve 8 over x squared, right? That's what that gold point is. So we're going to find out what x value they share. This point here, when 8x is equal to 8 over x squared. Does everybody see that? Does that make sense? So we're going to multiply through by x squared. On both sides we have 8x cubed equals to 8. Or when x cubed is equal to 1, or when x is equal to 1. So we know the x coordinate for that intersection point, that gold point, is an x value of 1. Same thing with this one, it's the same point, that's an x value of 1. What's the point in region 2? That point, the pink point.
8x is equal to x.
Right. That point is when the red curve 8 over x squared meets the purple curve, which is x itself. So when does x equal to 8 over x squared? Right, multiply through by x squared again. So we have x cubed on the left equals to 8 on the right. And then that occurs when x is equal to 2. So now we have the two regions, we have where each region starts and stops in terms of x. So the area of the first region would be the integral from where to where?
0 to 1.
0 to 1, right? This was an x value of 0. What's the height of each rectangle in that first region? Yeah, draw the rectangles. Rectangles have a height of top minus bottom, top function minus the bottom function, 8x minus x with respect to x. Oh, now we can just call that 7x plus region 2 goes from where to where? An x value of 1 to 2. Those are our intersection points. What's the height of each rectangle? Again, top minus the bottom. Top function is
8 over x squared
yeah.
minus x.
So that's the setup to find the area of that region. Any questions? Yeah.
So when you go to solve this, are you just plugging those values in? You just plug in the 0?
Well, yeah, we'll first find the antiderivative,
Fine.
and then we'll plug in. Yeah. I'll just rewrite it. Yeah, so let's go ahead and evaluate that. The first one was the integral from 0 to 1 of 8x minus x. So we're just from 0 to 1, it's 7x dx. And adding the area of the second region from 1 to 2. And that was 8 over x squared. So let's think of that as 8 times x to the negative 2 for the power rule, minus x dx. So the antiderivative of 7x is 7x squared over 2. That one's evaluated from 0 to 1. Plus, we've got add 1 over 1, negative 8 over x, minus x squared over 2. And all of that is being evaluated from 1 to 2. So this stuff, we've got 7/2 times 1 in there first, 1 squared is f of b minus f of a. We'll just keep those together. You know, if that weren't 0, then you need to combine this first, right? Because both of those things represent the area of that first region. And we have to take the area of the first region and add it to the area of the second region. All of this stuff is this stuff. Okay. So 2 into that antiderivative, we've got, let's write it like this, negative 8 over 2 minus 2 squared over 2. So that's f of b, right? That's the antiderivative evaluated at the upper limit. That needs to be computed as one thing. There's f of b minus f of a. And that's 1. That needs to be evaluated together. Then you subtract the 2. Then you add the result to what we have in this for the blue result. And ultimately, it doesn't matter now, since we're just adding and subtracting a bunch of things. It doesn't really matter what order you add or subtract. But you definitely need to be mindful that, especially like when antiderivatives involve a minus already, that's just there because that's the antiderivative. The fundamental theorem of calculus has you subtracting here. Does anyone have any questions about that? So, we're just adding and subtracting a bunch of fractions at this point. The answer is 6. Feel good on that? It's okay. So one question like this on the final, not one you have to split up the region though. There's 1 or 2 like that on your homework. That's kind of all we have time for. We're going to talk about the final very briefly. The final exam has, I forget how many problems. The problems are circled, so you've got 5 short answer, 1 problem where you evaluate the definite integral. But there's a total of 116 points. And these short answer ones are, something that you should in theory be able to answer pretty quickly, like the derivative of that function. Evaluating the definite integral using the definition will be provided, so that definition is this thing right here. You don't need to memorize that. You can't have that on your note card, so don't bother memorizing it or writing it down anyways. I will provide that. There's the Theorem 5.1 Part 2, by far the easiest way to evaluate those things. If you didn't get a handout in class, it's on D2L under handouts. You can see the examples we worked in our notes. Limits, there's 3 limits, they're very vague, but I will say that there are any limits that are of the form 1 to the infinity, 0 to the 0, or infinity to the 0. The reason I mention infinite limits is because these types of limits, for instance, the limit as x approaches 2 from the right on 1 over x minus 2, those, and just really be 100% sure when you can use L'Hopital's rule and when you can't. A limit like 1 over x minus 2 as we approach 2 from the right is not something you can apply L'Hopital's rule to because it doesn't evaluate to 0 over 0 or infinity over infinity. So these types of limits, the numerator is fixed, the denominator is approaching 0. These limits approach positive or negative infinity depending on what values you approach 0 through.
On the previous one, we can't have those on our note card, right?
Right, yeah, you can't have those theorems on your note card because it comes from chapter 5. But that's why I think that theorem is also more efficient to use, and I think the pattern is easier to establish or to remember. So hopefully that shouldn't be an issue. If you get stuck, come ask me. with that part. But yeah, it's pretty straightforward. I think everyone should be able to remember that fully. So these questions here where you have a piecewise function and you have to evaluate certain limits on, I hope those are pretty easy at this point. One question, there's 6 derivatives. One will be logarithmic differentiation and one will be implicit differentiation. The other 4 might be like a chain rule, a product rule, a quotient rule, stuff like that. But definitely one logarithmic and one implicit. And then using the stuff from chapter 4, finding intervals of concavity, increasing and decreasing.
Would we then graph a function after we found all that, or?
Yeah, you could. I don't remember. I don't think I have you actually graphing it on the final though.
Okay.
There's 4 antiderivatives. These antiderivatives could be U substitution, 2 definite integrals, one of those average values. This was from 5.4, the average value was 5.4, and one question where you have to find the position, velocity, and acceleration given the acceleration. Where did that go? Given A of t. And then one question from 6.2, the graph will be given, intersection points will not be given. So, I think I have, no I don't. All right. Yeah. So is there any general questions you might have? Remember, if you're gonna do the note card, you can have the front and back. That's totally fine. You can print it from your computer. Just please don't have anything crossed out on it. If you mess up and you're at the end and you don't want to redo your note card, cross it out, but show me before class, before the exam. Say, hey, I crossed this out. I think that's about it. If you have any questions, issues, whatever arises from now until Tuesday, please email me. I'll be around. Is there anything specific y'all want to look at in the next 4 minutes? All right.
No.
Well, so yeah, also look over the old exams too, and the keys are there as well. So. Yeah, I'll be in my office from 1 to 3 on Monday.
Hey, you can do that. I'm going.
I, because my wife